Okay, in Egyptian era, they have some formulas which is sometimes is very accurate and sometimes it's kind of not giving us the right answer but kind of close enough ones. So as you can see here, the first formula, which gives us the area of a rectangle, is not really accurate result, but it's kind of giving us close enough result for that. So let's just check whether this is really close enough for that or not, right? So let's, I just use some dynamic graph, dynamic geometric software to just sketch any kind of arbitrary quadrilateral. And sorry, this one returns the length of each side of this quadrilateral, right? So dA is actually is 1.6 inches, and that is 2.95 and 1.81 and 2.52. So key point is we don't care whether the opposite sides are parallel or any two consecutive sides are kind of orthogonal, like a perpendicular or something like that. We don't need any such information. According to this formula, all we need is just use those lengths of each side. So let me just assign A, B, C, D for them. Then it returns the result. So let's just calculate it. And this one is actually the result from that software. So that software calculates the area of this quadrilateral, and it says 4.6 square inches the area. Okay, then let's apply that formula here. So 1/4 of A plus C. So as you can see here, the key point for that formula is we have to add in the length of opposite sides. So 1.6 plus 1.81 and 2.95 plus 2.52. Okay, so please use your calculator, okay, to get the results. Sorry. Okay, but according to my calculation, the answer is 4.66, and that is close to 4.6. Okay, like that. So if that quadrilateral is not too big, then we might get very reasonable result from that formula. Okay, so that is just one simple example that how Egyptian people made their own formulas. Then it'll be really kind of good enough, especially for rectangle case. Then by that formula, we'll get exact result for that. Okay? So let's say we have the quadrilateral is actually rectangle. Then let's say this length is B for the base, and that is for W, okay? Width or whatever. Okay? Then according to that formula, the Egyptian formula, it should be 1/4 times A plus C, right? So we need to add the opposite side, which is 2W times B plus D. So that is 2B. So when you multiply them, we have some 4 times W and B. So it's base times height, or the length times width, whatever. So that's exact same formula we had. Okay? So let's go to next one. So the previous one has some kind of errors, but this one is actually giving us another kind of nice result. Okay? And this one is about the measure, the, the area of a circle. And according to their formula, their method, it's simply just to subtract 1/9 of the diameter from the diameter. sorry. So it's kind of d minus 1 ninth d. So it's kind of 8 nines times d and make it square for that. So that's the formula. Okay, so please just try to check to have any circle and apply the method here. But in this next example, what we are interesting about that is, okay, they didn't know about pi, right? Then, according to this formula, how close they got for this pi, right? So instead of pi, what number they use to calculate the area? Let's just check that part. So for that, according to their formula, the area of the circle is 8 nines d squared. Sorry. Okay, but we have a formula for that, which is pi r squared. So let's just compute these two. Then we have pi r squared, and we assuming maybe they are same, but kind of close enough to this one by their formula. And there is it's gonna be 8 nines times, now d is the diameter, right? So it's gonna be 2 radius, right? 2r, and make it square. So there's 16 over 9 r squared, which is 256 over 81 r squared. So when you compare our own formula with Egyptian formula, after cancel out those r squared, we could see they use 256 over 81 for pi. We know pi is a rational number, but 256 over 81 is rational number, so there must be some error. So it might be interesting, right, how big this error is, right? So please try to calculate that one and try to see how close these two numbers are. So is it like a 3.057 or 3.1 and 75, right? How close these two numbers are. Okay? Okay, so we found out those two formulas are not accurate one, but kind of close enough. So next one is actually they have really accurate formula for some cases. And as you can imagine, it's Egypt, right? So they know the formula, the exact formula to measure the volume of a pyramid. And if not the entire pyramid, if you just cut off the top part of the pyramid, they still could calculate the volume of that remaining portion of it. And their formula is like this. And the condition for that is A is for the length of this bottom, this length of the side of the bottom. Actually, it's square, right? That's our assumption. And B is the length of the side of the top part. And H is the heights of that remaining portion. So you can get that one from center of the top square to the center of the bottom square. And that is our H, right? So question is it a really accurate formula, right? So through the next example, we want to show that is actually the accurate one. Okay, so let's follow our assumption. The length of the bottom side is A, and that top part must be B, and we know that height of this portion is H, right? So let's just assume that if we have the original pyramid, right, and the height of this removed part, let's say it's X, because we don't know. Okay. Then when you look at this top part triangle, And all together, we know these two triangles are similar, which means each corresponding sides must be proportional to each other. So the height of this small triangle is x, and the height of this larger triangle is x plus h, right? Then that ratio must be equal to the length of this bottom of the triangle and the length of the bottom of this bigger triangle. So let's just write down that form, the ratio. X to B, that's the relation between those two, has to be same as x plus h to a. Or we can say x over b equals x plus h over a. So by cross multiplication, ax equals b times x plus h. Our goal at this moment is looking for the x value, right? So let's just arrange it for x, which means we want to put any terms with x all together. So ax minus bx equals bh. So a minus bx equals bh. Therefore, the height of that removed portion of the pyramid will be bh over a minus b. Okay. Then the next question is, what is the volume of the entire pyramid? Then by the formula for the cone shape is a 1/3 of the base times height, right? Okay, so you can imagine like if you have those type of cylinder, right? Then the volume of that is the base, whatever that is, times height, right? But if it's a cone shape out of it, then it becomes 1/3. It's always like that. So by that method, the volume of the entire square pyramid, not the, including remove part altogether, that volume must be 1/3 times base is the square of a, right? And the height for that is entirely is x plus h. Okay? But we know what x is, so the entire volume for the entire pyramid should be 1/3 a times bh over a minus b plus h. Okay, so that's enough. Then what is the volume of this discarded part, the removed ones? Then it's 1/3, and at the time, the base should be this portion, right? Like that. So it's going to be b squared, and for the height for that portion is just x. This one, but we can change that one to using this one, right? So instead of x, we put bh over a minus b. Or simply, we can say b cubed h over 3 times a minus b, whatever. Okay, okay, so then it's asking, find the volume of the truncated square pyramid, which means the actual volume for what we are looking for. Then from there, it's clearly we want to subtract this removed portion from the entire one, right? So the volume of that should be volume of the entire pyramid minus, let me put 1/3 side, it's b cubed h over, I already used 3, so a minus b. Okay. So let's say it's just a minus b is just for everywhere, so let's just make common denominator. So 1/3 and a times bh over a minus b plus 1/3 a squared h and minus 1/3 b cubed h over a minus b. So this one doesn't have a minus b in there, so let's just make that. Then it's 1/3 a squared bh over a minus b plus 1/3 a squared h times a minus b over a minus b, right? We just put the necessary expression at the numerator and denominator. Then 1/3 b cubed h over a minus b. So we have a minus b as a common denominator, including 3, right? So we can put 1 over 3 a minus b and put all the other remaining ones. So a squared bh from the first term and a squared h a minus b from the second term and minus b cubed h from the third one. So let's just simplify all this. Then it's a squared bh plus a squared ha minus a squared hb by distribution law and minus b cubed h. Then a squared bh minus a squared hb canceling out each other, and we only have that term, right? So it's going to be 1 over 3 a minus b, and this one is a squared times a, right? So it's going to be a cubed, and that is b cubed, and h is a common factor for both. So let me factor out h, and the remaining one is a cubed minus b cubed, right? Now in algebra, we know that a cubed minus b cubed is a minus b times a squared plus ab plus b squared. You should remember that. And another one, very close one, is a cubed plus b cubed is a plus b times a squared minus ab plus b squared. Okay? But anyway, right now we just need this one. So apply that here. Then we got h over 3a minus b. Then instead of a cubed b cubed, we can put a minus b times a squared plus ab plus b squared. Then these a minus b's are canceling out each other. Then we have 1/3 times h times a squared plus ab plus b squared. And that is the formula that division people has. Okay, like that.